Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2015 Physics Unit 2 Paper 2. And so it's a question 5, and it's a question about logic gates. And so 5A says, draw the truth table for a 2-input NAND gate. All right, so the first thing we want to do is draw our NAND gate. So here's my NAND gate here with 2 inputs, A, B, and an output, C, right? So here are my 2 inputs. If I have A and B both being 0, right? If this were an AND gate, 0 and 0 would have given me 0. But because it's a NAND gate, it's going to give me 1. Okay? If I have 0 and 1, let me just write these on as I'm talking. So if I have, put them in a different color. If I have 0 and I have 1, if this were an AND gate, that would have given me 0. And so because it's a NAND, it will be 1. And so that's what we see here. Okay, let's look at the third case where we have A being 1 and B being 0. Again, 1 and 0 in an AND gate would have been 0. Well, because this is a NAND gate, I'm going to get 1. And so that's what we see here. All right, let's do the final one now. For the final one, A and B are both 1. So 1 and 1. If this were an AND gate, it would have given me 1 because they're both 1. But because it's a NAND, I'm going to get 0. Remember, the NAND gate inverts whatever you would have gotten from your AND gate. And so that's going to be 0. So 1, 1, 0. And so that's our truth table, right, for a 2-input NAND gate. All right, so let's go ahead now. Move ahead. So 5B says, complete the table below for the circuit shown in the figure and hence show that this circuit is equivalent to a NAND gate, right? Show that it's equivalent to a NAND gate. We had the truth table for a NAND gate earlier. So let's just kind of go back and just look at that real quick again. Just look at that again real quick. So this is what we're expecting for our final output. We're expecting 1, 1, 1, 0. So let's go ahead, fill out this truth table, and hopefully our F is equivalent to our C on the previous side, okay, or the previous question. So let's go ahead with this one now. So let's start with our 2 inputs, A and B being 0, right? So if I start with A and B being 0, 0, 0, 0, right? This is coming into an OR gate, but it's the only input coming in, so it's just gonna get inverted. It's a NOR gate, right? So it's coming into a NOR gate, so the 0 is just gonna get inverted and become 1. So C will be 1, and this 0 is coming into a NOR gate. It's gonna get inverted and it's gonna become 1, right? So now my C and D are 1 respectively. So I have 1 and 1 coming into a OR gate, a NOR gate, right? If it was an OR gate, that would have given me a 1, right? But that 1 is going to get inverted because I have a NOR gate and E will be 0. So I'll have a 0 here. And so 0 is coming into a NOR gate. It's going to get inverted and become 1. So F is 1. So we're on a good path so far. All right? So let's clear all of this and go again with our second set of values, second set of AB inputs, right? So say I use A to be 0 and B to be 1. Again, this is going to get inverted when it comes through this NOR gate to 1. So that's, I'm going to put a 1 here. So that's 0, 1. So C will be 1. And then the B will be inverted to become at D 0. And so I'm going to put 0 there. So now I have a 1 and a 0 coming into a NOR gate. A NOR gate. The 1 and the 0 in an OR gate would have been 1, but because it's a NOR gate, it will be 0. So my E is 0. So the 0 is coming into this NOR gate now. E0 is coming into this NOR gate. It's going to get inverted and become 1. So F is 1. All right. So let's try another set of input values for A and B now. Let's try, where are we now? Let's try 1, 0, right? Let's try A being 1 and B being 0. So 1, 0. So when the 1 comes in up here, it's going to get inverted and it's going to become 0. So we're gonna put a 0 for C. When the 0 comes in here, it's gonna get inverted and become 1. So we're gonna put a 1 for D. So now we have a 0 and a 1 coming into a NOR gate. If this was an OR gate, the 0 and the 1 would have given us 1, but because it's a NOR, it's gonna give us 0. So E is 0, so I'm gonna drop 0 here. The 0 comes into this NOR gate, it's gonna get inverted, and so my 0 will now become 1. So my F is 1. All right, the final set of values for A and B now are gonna be 1, 1, when they're both 1. Okay? So put in 1 here, putting in 1 here. So let me just put it in the table as well. When the 1 comes through, the NOR gate is gonna get inverted and become 0. So I'm gonna put 0 here. When this 1 comes through the NOR gate, it's gonna get inverted and become 0. So I'm gonna put the 0 here for D. Now what we have coming into this NOR gate is 0, 0. If this were an OR gate, this would have been 0, but because it's a NOR, it's gonna be 1. It's getting inverted, so it will become a 1. So I put a 1 here. Now I have a 1 coming into a NOR gate as my only input into this NOR gate. It's gonna get inverted and become 0. So look at what we have now. We have when our input is AB, 0, we get 1. 0, 1, we get 1. 1, 0, we get 1. 1, 1, we get 0. And this is exactly the same as for what we saw in our NAND gate case earlier. And so this truth table shows that this circuit is in fact functioning as a NAND gate. Okay? All right. So with that, now we're going to go ahead. Let's clear this. All right. So now we're at 5C. 5C says, draw the NAND gate version of an SR flip-flop, taking care to label all inputs and outputs, right? So an SR flip-flop is a set reset flip-flop. Let's just write that here. So it's a set reset flip-flop. It has 2 stable states, right? And so we say that it's bistable, okay? So it's a bistable device, or a latch is what we call these flip-flop circuits, okay? So this is a set reset flip-flop, 2 stable states, bistable. It can exist in an OR gate, NOR gate version as well, right? There could have also been a NOR gate version, but we're being asked explicitly to draw the NAND gate version. And so here's a NAND gate version. This is what it looks like. So here's our NAND gate version of a SR flip-flop, right? Here is our input. Our set input is right here. It comes through, and then it gives you an output Q. That Q gets fed down into here where your R input is, and together that's gonna give you a Q bar. So your Q bar is the output from your reset input, and then the Q is the output that you get from your set input, okay? So it's kind of like feeding back. So this feeds back up here, right? And those are 2 that you're comparing to determine what the output will be. And then this output feeds down here. And so you're comparing those 2 to see what the Q will be. So it's really a nice little loop that just keeps going, right? Really flip-flopping back and forth. Okay? So this is what we would expect it to draw for the NAND gate version of our SR flip-flop. Keep that in mind. So keep in mind that there's a NOR gate version as well. This is the NAND gate version. And that's what we're asked to draw here. All right, so let's go ahead now. All right. So what I did was I went ahead and I completed a truth table for this SR flip-flop using the NAND gate, right? So I did a truth table for that. And so just take note of these values here. When this is 0 and this is 0, we're gonna be in what we call a latch state. So the flip-flop will latch on to whatever the previous value was. And then 0, 1 would be 1, 0, right? That's when we have this state here. And then 1, 0 is 0 for the Q output, and then 1 for the Q bar. And then 1, 1 we call invalid, or like a metastable state. It's like unstable up there, okay? All right. So just keep this truth table in mind. In fact, I'll bring it up for our next question, okay? So here we are. We have our NAND gate version, and we have a truth table that goes along with that, which is always very important to have a truth table for whatever our circuit is, okay? So here's our truth table. Let's go ahead and see what is being asked of us. So 5D now, the last part of this question says the signals S and R, so that's your set and your reset signals, shown in the table below. Well, actually, this is the figure that we're looking at, are simultaneously applied to the corresponding inputs of an SR flip-flop. Determine and draw on the figure below the Q output. So we're supposed to just draw this guy, the output that would be coming from the S. And then that would indicate that the flip-flop is set, right? Because we're drawing the output that's coming from the S of the flip-flop for the time intervals 1, 2, 3, 4, and 5. So we're given time intervals here that we're working with, right? And we're supposed to draw what the Q would look like in each of these, for each of these specific input, right? So this is our truth table. So we're going to compare what is being shown on the timing diagram with our truth table, and that's how we will know how to fill out down here, right? So we're going to use our truth table as a guide, and we're going to compare to what the question says the inputs are. So we're going to start out here. Let's start out here, right? And then we'll jump into the time interval 1 and proceed. So let's start out here, right? When we start out here, what do we notice? We notice that the S is at a level 0. It's low. It's in that low state. Whereas the R is also in a 0 state. So they're both low. And so if I were to draw something for my Q, that would be in a latch state. So it would also be 0. So I'm just going to put 0 down here. Draw a 0, a line representing 0, a low state for Q, right? So now, when we enter into time interval 1, what do we see? We see that the S is now 1. It's in a high state. And then the R remains in that low state 0. So then I look at my truth table and I see that when it's 1, 0, my Q is supposed to be 0. So I'm going to keep my Q low. Okay, that's what my truth table said. When I have 1 and 0, I should keep my Q low. Okay? So let's come over here now. We see that S is now low and Q and R is also low. So 0, 0, they're low. It's a latch, so it will latch on to whatever the previous value was, which is 0. So it will still be 0 at that point. Okay? So now, when we come to this point, we're still at a 0 for our S, but then the R is now 1. So we look in our truth table, we're looking for S being 0 and R being 1. S being 0 and R being 1, and we see that Q is 1. So we have to show Q jumping up to 1 in that region there, okay? And then over here now, we have a 0, 0. So that's a latch state. So the system will hold on to whatever the previous value was, which was 1. So we'll still have a 1 for this remaining time in the time interval 2. So 0, 0 is a latch, so we latch on to the 1 that we had from before, so we stay there. Okay? So now let's look at time interval 3. In time interval 3, the S is at a high state of 1 and the R is at a low state of 0. When we're at 1, 0, what's happening? 1, 0, Q has to be 0. And so Q has to drop back down now to 0 for this time interval. Okay, now let's look at time interval 4. In time interval 4, right? In time interval 4, S is 0 here, and then here, R is 0. So it's a 0, 0, so it's a latch state. So it will hold on to the 0 that it had right here. Okay, so hold on to the 0 that it had previously in this latch state of 0, 0. Now, what happens in this same time interval of time interval 4, this stays 0, but then this one jumps up to 1, right? Whenever we have a 0, 1, so S is 0 and R is 1, what do we have? Q has to jump up to 1. And so Q will then jump up to 1 again. And now we're entering time interval 5. So in time interval 5, we see that we are in a 1, so S is 1, right? And what's happening to R? R is also 1. So R stayed at 1. So we have a 1, 1 that's an invalid state, an unstable state. And so what's going to happen? The system is just going to stay latched in where it was before. So we'll still have it being at 1 up here. Okay, so in 1, 1, we stay where we were previously, which was at 1, and so we stay there. And then finally, this is the exit portion. This is not necessarily important because they only said 1 to 5, but let's look at it. This would be 0 now, and that's 1. So that's a 0, 1. 0, 1 means that we stay at 1. So we're going to stay at 1 for the first part here, and then we're still at 0, and then this guy drops down to 0. So we're in a 0, 0 latch. We're going to stay where we were, which was at 1. Right? And so with that, we've completed this timing diagram here. So the important thing to remember about timing diagrams is that you're going to be using your truth table as a reference, and you're going to be looking at what the diagram is telling you that the inputs are, and then you're going to compare those values to your truth table values, okay? So here we saw 1, 0. We look for 1, 0. We knew that we had to be in the 0 state. 1, 0, we knew we had to be in the 0 state. 1, 1, we're going to latch on to whatever we were previously. And previously here, this was 0, 1, and 0, 1 is a 1. And so we see that being 1 there. And also here, 0, 1 is a 1 for Q. And so we see there being a 1 here. Okay. And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel. And if you look on the left here, you'll see the next video up. And if you look on the right, you will see our Module 3 playlist, where you'll find tons more interesting content that will be helpful in getting you ready for this exam, okay? So thanks for watching, and we'll see you in the next video.